We've done substitutions. Time to talk eliminations of alcohols. Remember, alcohols have terrible, horrible, no good, very bad leaving groups. So when you have acid, you want to protonate them first. So this time we protonate and we say, ooh, this is a secondary alcohol. And secondary alcohols like to make carbocations. So after I protonate my alcohol to make water, that water leaves to leave behind a carbocation. That carbocation, if it were in acid like HI, or acid like HBr, or acid like HCl, it would have to have zinc, remember. If it were in those acids, these conjugate bases, I minus, Br minus, Cl minus, those conjugate bases are good nucleophiles. So those conjugate bases do substitution. But HSO4 minus is not a good nucleophile. Why is it not a good nucleophile? Well, one reason it's not a good nucleophile is because that negative charge, is it localized or delocalized? That negative charge is delocalized to these other doubly bonded oxygens in this Lewis structure through resonance. You can draw resonance structures where this oxygen up top is negative. You can draw a resonance structure where this oxygen at the bottom is negative. That lone pair, that negative, is not localized. Anytime you have a delocalized lone pair, that is not a good base and not a good nucleophile. Things that are not good bases are generally not good nucleophiles. So one reason is that oxygen's got a delocalized lone pair. Also, this group overall, this conjugate base overall, is a bulky compound, and bulky things are not good nucleophiles. Remember, Katbu is a better base than it is a nucleophile. Naomi is a better nucleophile. So both Katbu and Naomi, let me write those to make sure we're on the same page here. Katbu and Naomi. Yes, officially I should have the NA and the K. Katbu and Naomi, this thing is very bulky, so it's good at plucking a hydrogen rather than attacking a carbon. This thing is not as bulky, so it's good at plucking a hydrogen or attacking a carbon. Smaller things are better at attacking and plucking. Big things are better at plucking. So, this big thing, not a good nucleophile. It's better to take a hydrogen and do an elimination. Okay. So we're going to do elimination when we have a base like sulfuric acid, because the conjugate base of sulfuric acid is not a good nucleophile. So what we're going to do is take a hydrogen. The position where the carbocation is my alpha. Next door, I've got beta carbons. If I take a beta from the left, that's a Zaitsev beta. Take that hydrogen, dump in electrons, and I get this product. This is an E1 mechanism that I'm drawing. I'm making a carbocation, and I get an elimination product out of it. In E1, are there stereochemistry requirements? No. So rotation could happen around this bond, and you take a different hydrogen, the other hydrogen that's connected here, let's say that one, and you end up with this product. Yep. The top one is an E isomer. The bottom one is the Z isomer of the same alkene. So both of those are 2-pentene, but the top one is E2-pentene. The bottom one is Z2-pentene. This will make both. And remember, when carbocations are involved and you're doing elimination, you don't only get Zaitsev, you get anti-Zaitsev also. We'll take a hydrogen from that terminal beta to make us this product. It's not E, it's not Z, it's not applicable. So we get 3 constitutional isomers out of this reaction. Those 3. The 2 red ones are officially major because they're Zaitsev, but in fact, I would even go so far as to say the E Zaitsev is major because big stuff likes to have its own space. Big stuff close together is not great. Okay, one more thing to highlight before we walk through a little more stuff. Why did I use water to take this hydrogen instead of this conjugate base? Well, it has to do with acidity. Oh man, water has the conjugate acid H3O+. Sulfuric acid, or this bisulfate, HSO4-, has the conjugate acid H2SO4. Which of those acids are stronger? Sulfuric acid is stronger, meaning water is the stronger base. And you might say, but where did water come from in this whole reaction? Well, water was not added as a reagent officially because you want to avoid having water in this mixture because you're trying to get rid of water. Note, you got rid of an OH here and an H on a neighboring carbon. You got rid of water overall in this transaction. Your products were the alkene and water. The sulfuric acid acts as a catalyst, but the real reason I took water to deprotonate that H instead of HSO4- is because water is the stronger base. The water in the solution you can think of as coming from the leaving group there. So a proper E1 dehydration mechanism does not use HSO4- to deprotonate the beta hydrogen. It uses water to deprotonate the beta hydrogen. Yep. Yeah. Okay. So this says H3PO4 or BF3 can also be used. The thing that these two have in common is they're both acids that have bad nucleophile conjugate base. Yeah, HSO4-, terrible conjugate base. Like super weak nucleophile. H2PO4-, super weak nucleophile. Big bulky acids like that have bad conjugate base, have conjugate bases that are bad nucleophiles. That's what I really mean. BF3 is going to do a similar thing. It's a good Lewis acid. It's not a Bronsted acid, but a good Lewis acid. It would be used to turn your O into a better nucleophile. It would be used to turn your O into a better leaving group, your OH into a better leaving group. We're not going to draw that mechanism, but we could if we needed to, but we're not going to. This says, how do you maximize yield? How do you ensure that you get the maximum amount of product possible in this reaction? Remember, I said we also have water as a side product here. If you go back, way back in your general chemistry knowledge, there's a thing called Le Chalier's principle that says if you stress a reaction, if you stress a system, the system will respond. What? If we're cooking an alcohol with a catalytic amount of acid, like sulfuric acid, cooking an alcohol with a catalytic amount of acid, we get an alkene and water as a byproduct. One of Le Chalier's principle says if you remove a product, the reaction will shift to make more of that product. So note that this is an equilibrium process. You establish equilibrium between these things, and if you remove one of the products, equilibrium will quickly be reestablished by making more products. If you remove more products, equilibrium is quickly reestablished to make more products. If you remove more products, equilibrium is quickly reestablished to make more products. So Le Chalier's principle can be taken advantage of here in that if we are somehow able to remove water from our reaction, we can force this reaction to go to completion. We can force all of our alcohol to be dehydrated to one of these alkene products. Additionally, if we could somehow remove the alkene product, we could force our reaction to favor, force our reaction to create all products. All of our alcohol will be consumed if we can remove our alkene or our water, or potentially both. One way that this is done in organic chemistry labs is through distillation. Distillation is a way to separate things based on boiling point. Well, this alcohol has hydrogen bonding. This alkene has a none. This alkene has dispersion forces. So in general, something that has dispersion forces, especially if they're similar molecular weights, something that has dispersion forces will have a lower boiling point than something that has hydrogen bonding. So what you can do in an organic lab, if you're trying to dehydrate an alcohol, is you cook it in a distillation setup, and your alkene gets removed from your reaction flask by distillation, while your alcohol stays in the reaction flask and continues to create more alkene. And eventually, if you remove all of the alkene, equilibrium keeps being established again and again and again to make more and more alkene. Eventually, if you remove all the alkene by distillation, all of the alcohol will have been consumed as well. So, yeah, Le Chatelier's principle. It's a thing that we will talk a lot about in lab stuff, but I think it's worth mentioning in this lecture stuff for now as well. All right. So that's dehydration of an alcohol in acid, but you could also use Pockol with pyridine, POCl3, Pockol with pyridine. Pyridine is what? A weak base. So that weak base is going to shift your mechanism. We'll talk about it. Give me a minute. In general, dehydration happens through an E1 mechanism. In general, alcohols are dehydrated through E1. That's most of the time we're going to see secondary and tertiary alcohols doing dehydration. If you have a primary alcohol, you're going to do intermolecular dehydration. That's going to be through an E2 mechanism, but there are some caveats to that I think we should talk about. So here's a primary alcohol. If I'm wanting to dehydrate this guy, I first protonate my OH to make a better leaving group. I got it. It's water connected to my carbon. And then this intermolecular dehydration, what does that mean? It means that another alcohol molecule that has not yet been protonated is what's responsible for taking the hydrogen from the beta carbon. This step is E2, right? That's a concerted mechanism, E2, and I get this alkene out of it. However, one reason that I just explained all that distillation and heating and Le Chatelier's principle stuff is this product is generally not the observed product of this reaction. The observed product in this reaction is this. What? How does that happen? Well, when you're refluxing this, when you are heating this mixture, this primary alcohol and sulfuric acid, heating it, when you're heating it and heating it and heating it, yeah, it's going to make this alkene. But alkenes in the presence of acid, like sulfuric acid, especially if they're marinating in sulfuric acid for a long time, you're going to protonate that alkene just like we've seen before and make a carbocation because you could make that stable secondary carbocation. Through a thermodynamic equilibrium process, this carbocation can then undergo elimination to make my major Zaitsev product, this purple thing. Yep. So primary alcohols are weird things to dehydrate. They don't give what one might expect as the typical product. The product appears to have gone through a carbocation because the product seems to have shifted from where the alcohol originally was. It does not go through a primary carbocation. It does not go through a primary carbocation. What really happens is you do an initial elimination. That alkene then gets protonated to a more stable carbocation that can then undergo a second elimination. So this is a weird little mechanism that our first bit was an E2, but this last little bit is an E1 that goes through a carbocation. Super strange, I know. Primary alcohols are not something we see dehydrations of a lot. Since dehydrations in acid can sometimes cause issues, sometimes you want to dehydrate in base. Like this, Alcohol with pyridine. So this says, page 473 is the mechanism. I guess I'll draw it for us now. POCl. Oxygen, terrible, horrible, no good, very bad leaving group. So you got to make it better. And one way to make it better is attack the phosphorus. Like so. POCl. With plus. What is pyridine? Pyridine is a weak base. And the purpose of that weak base is to clean up that hydrogen to make a neutral oxygen species. It's real crowded down there. Pyridine can also, and does also, serve as your base to pluck a beta hydrogen. This is my alpha. Here's my beta. Pyridine plucks that beta hydrogen. Why am I drawing that mechanism like it's concerted? Because it is. E2 is favored when you have base. And this is definitely a reaction in base. I've shown it as a primary alcohol reacting with alcohol and pyridine, but this elimination, this E2 elimination with alcohol and pyridine could happen with primary alcohols, secondary alcohols, tertiary alcohols. It doesn't matter. But the point is it goes through an E2 elimination. The reason I chose to draw it with this primary is that this is the one and final observed product. Remember our last example showed that we made that product 1-butene initially, but then it equilibrated to this 2-butene with alcohol and pyridine because it's a basic mechanism under basic conditions. We get this 1-butene as the actual observed final product. Yeah? There's a note behind there. Basic conditions. No carbocations, no rearrangements. Yeah. Cool dudes. Yeah, I like it. Which alcohol dehydrates the fastest? What's the real underlying question here? Which alcohol would create the most stable carbocation? The reason I can automatically go there is we talked about kinetics and rate determining step as it applies to carbocations. So I need to assess what kind of carbocation each of these would make. This first one would make a secondary carbocation. The second one on the right here would make a secondary carbocation. The third one down at the bottom would make a secondary carbocation. Oh boy. And the last one would make a secondary carbocation. That's not helpful so far. Do any of those get a secondary designation like allylic, benzylic, aryl, and vinyl? Yeah. The top right corner is also benzylic, would also make a benzylic carbocation. The bottom left is benzylic, and the bottom right is aryl. So already I can say 1, 2, 3, 4, just giving these, maybe I should have given them letters, but I can say 4 is the worst because aryl carbocations are terrible. Number 1 is next because it's not benzylic. And then between 3 and 4, nope, between 2 and 3, I need more information. This group has a benzylic lone pair. What does that do? If I'm imagining that hydroxide, that OH being gone, and the carbocation being here, that oxygen can donate electrons like this to help stabilize that carbocation. These pi bonds could also donate to help stabilize that carbocation, but the one with the oxygen is helpful because you end up with a resonance picture that has a complete octet, and that's great news. So that leads me to say that number 3 is very, very, very stable, but it's not as stable as number 2, which has this extra electron donating group. Remember, electron donating groups make carbocations more stable. Electron donating groups make carbocations more stable. Yep. There's a reason we go through this example just before talking about this. This thing is something that I really love for students to discover on their own what happens. And I really think that process of trying to figure it out on your own is super valuable. However, I traditionally make students do that during the lab period, and, well, we don't have one of those. So when I have a vicinal diol, what does it mean to be vicinal? On neighboring carbons. A vicinal diol, I meant to show this before I started drawing and I forgot. A vicinal diol is this vicinal diol will undergo a dehydration reaction. It will make a C6H12O product. This reactant is C6H14O2. We lose water in the process. But how do we lose water? Well, obviously, you protonate one of the OHs. These are equivalent OHs. They would both make a tertiary carbocation. Protonate one of the OHs. Let the leaving group leave. And we make a carbocation. It's a tertiary alcohol. Tertiary alcohols make great carbocations, like that. That tertiary carbocation could eliminate a hydrogen next door to make an alkene, but that's not actually what happens. What? Yeah, remember this acid is not going to do substitution. This acid is going to favor elimination. So what happens? I don't understand. What happened was a methyl can shift next door. And you say, why the heck would a methyl shift next door? That turns my tertiary carbocation into a secondary carbocation. What? I don't get it. Well, that secondary carbocation has an oxygen connected. And that oxygen that's connected has a lone pair. That lone pair can donate by resonance to give you a doubly bonded oxygen, like that. And then water can come clean up that hydrogen to give you a ketone product. Not an alkene, but a ketone product. Yeah. Vicinal diols always rearrange. Did you hear that? Vicinal diols always rearrange. They always rearrange in such a way that one of the alcohols leaves, whichever one would make the best carbocation, one of the alcohols leaves first to give you a carbocation. Then there is always a shift. What kind of shift? It could be ring, it could be hydride, it could be methyl. There's always a shift that comes next. That shift always happens to move something from the carbon connected to the oxygen remaining so that you have a plus on the carbon that's directly connected to the oxygen. The reason you would want that is because the resonance of these things is great. If we were comparing these two resonance pictures, which one of these contributes most to the hybrid? Which one of these is the winner chicken dinner most stable, bestest resonance picture? The one on the left, the one on the right? The one on the left is better than the one on the right because the one on the left is a structure where everybody has an octet. So vicinal diols always rearrange, and they always rearrange in such a way that you create a resonance picture where everyone has an octet. It's a carbonyl compound that's always created. That carbonyl compound in this case is a ketone, but it could be an aldehyde as well. So yeah, vicinal diols, they do weird little things, but we have to recognize that anyway. But you can. I believe you. I believe in you. That's eliminations of alcohols. Oxidation's next.